Hello, my name is Zachary Johnson, and I will be presenting some of the work during my PhD at Utah State University. Here, I will discuss some of the remote processes driving the Pacific Decadal Oscillation, or PDO, specifically how the Atlantic Ocean variability can remotely impact the PDO. First, I would like to thank my colleagues, Yoshi Chikamoto, Simon Wang, Mike McFadden, and Takashi Mochizuki. Before we jump into how the Atlantic remotely impacts the PDO, first, let's briefly review the PDO. The PDO is defined as the leading EOF of North Pacific sea surface temperature anomalies. And here we can see the sea surface temperature anomalies regressed on the leading EOF principal component. Many processes contribute to the PDO, including remote forcing from the tropical Pacific through the atmospheric bridge and subsequent changes in Aleutian low variability. Research suggests ENSO can remotely be forced by the Atlantic through interbasin interactions. So the question arises if we can quantitatively assess PDO variability that originates from the Atlantic basin. To help answer this question, we conducted several experiments where we assimilated ocean temperature and salinity anomalies into the ocean component of fully coupled climate models, the CESM and MIRAC. To identify the remote forcing from the equatorial Pacific and the Atlantic, we constrain ocean temperature and salinity anomalies solely in the equatorial Pacific and solely in the Atlantic. So first, let's look at the remote forcing from the equatorial Pacific. On top, I show correlation plots of sea surface temperature and sea level pressure anomalies 5 months leading the PDO in our equatorial Pacific experiment. The bottom plot shows precipitation in colors, upper tropospheric stream functions and contours, and wave activity flux in arrows. These plots highlight the atmospheric bridge process influencing the Pacific Decadal Oscillation through El Nino-like sea surface temperature anomalies and an enhanced Aleutian low. But interestingly, when we look at our Atlantic experiment, where we only assimilate Atlantic Ocean information, we see a similar Pacific process, El Nino-like warming, the atmospheric bridge, and an enhanced Aleutian low. So how does the Atlantic trigger the Pacific climate response? Well, here I show a Hofmolar plot of sea surface temperature and sea level pressure anomalies on left, and precipitation and upper tropospheric zonal wind anomalies on right. And this is averaged from 5 south to 5 north and correlated with the PDO index. The Atlantic impact on the PDO signal is first noted in the negative sea surface temperature and positive sea level pressure anomalies in the tropical Atlantic 36 months before the mature stage of the PDO. These positive sea level pressure anomalies propagate toward the Indo-Pacific sector, and this accompanies reduced precipitation over that region. We can see compensating warmer sea surface temperature, increased precipitation in the central and eastern tropical Pacific through Bjerknes feedback. We can clearly see the modulated Walker circulation in the Atlantic experiment by the upper tropospheric zonal wind anomalies. Also in our experiments, we discovered a pathway outside of the equatorial region in the northern tropics, and this involves the Atlantic multi-decadal oscillation, or AMO. Here on the left, I plot sea surface temperature and sea level pressure anomalies correlated with the AMO with a 12-month lag. So we are looking 12 months after the AMO in these plots. On the right, we have precipitation, stream functions, and wave activity flux. So in our Atlantic experiment, we see the AMO accompanies negative sea level pressure anomalies and increased precipitation in the North Tropical Atlantic. And we see Rossby wave propagation toward the North Atlantic and similar but opposite phases in the Pacific. So now I show a Hofmolar diagram averaged from 10 north to 20 north, where we saw the precipitation band in the previous plot. So during the positive phase of the AMO, we see increased precipitation in the North Tropics that extends into the Eastern Pacific. We also simultaneously see lower pressure emerged in the North Tropical Pacific and decreases in precipitation. These changes in the Pacific climate from the AMO provide the energy source for the Rossby wave propagation to the North Pacific, as we saw in the previous plot, thereby impacting the PDO. We find that 12 to 29% of PDO variability originates from the Atlantic, and this occurs through 2 pathways: the equatorial pathway and the North Tropical pathway. These results are published in a recent paper in Climate Dynamics. Thank you for your time.